Good morning everyone, thank you for joining me for this video. I am Mr. Ish. We are looking at a topic over here that's generally considered a bit confusing or difficult to understand, when in reality it isn't. I'm going to present this topic in a way that I wish it had been presented to me so that I would have understood it rather than superficially breeze through it when I was going through college. And with the lack of understanding, I went through these topics and did not do too well in them. But now I'm going to present it to you in a way that I wish it had been presented to me. We're looking here at position, velocity, and acceleration in a generalized manner with regards to integrals. And these are basically position, velocity, and acceleration to do with integrals of rate of change. If you think back to the fundamental theorem of calculus and to integrals and derivatives, S of t, if you're looking at a position of an object, and that's how you would annotate it, S of t, the position of an object, you know it has something to do with the distance or the displacement of that object. Anyhow, the position of an object, if you do its derivative, you end up with the derivative of this position, which is also equivalent to the velocity function. So if you start with a position function, you do its derivative, you end up with a velocity function. If you take this velocity function and you do its integral, which you know based on the fundamental theorem of calculus, you can start with a function, do its integral, and take the derivative of the antiderivative and back to your original function. Or you can start with a function, do its derivative, and then take the integral of that derivative and back to your original function. That's what this loop over here means. The position function by means of its derivative yields a velocity function, which by means of its integral goes back to the position function. Down here, if you have a velocity function and you do its derivative, you end up at the acceleration function. But if you do the integral of the acceleration function, you end up back to the velocity function. And it is by means of this cycle that you will address these type of problems which relate to position, velocity, and acceleration. An important tip, whenever possible, always try to graph your function because it will enable you especially to deal with these type of questions. The only reason being why you want to focus in on graphing is because when you're dealing with the concepts of displacement and distance, we're thinking about nets, like a net displacement or what the total distance was, and there's a big difference between that. If hypothetically you had a graph which kind of represented the, let's be generalized over here, which kind of represented the position of an object, but you're looking at the velocity function over here, and you know the integral of the velocity gives you the position. But when you graph this velocity function, you have areas between curves or areas below curves which represented the position. If hypothetically you have something which looks like this, you know you have an area below this curve, we'll call this A1. You have an area above this curve actually, which is called A2, and you know if you look at the net area, it would be A2 minus A1, or you can say A1 minus A2 and bring in absolute values. If you do the net area calculation by means of integration procedure for a velocity function with regards to our studying a position, we're looking at here at displacement, or the net displacement is where was the object at its original point and where it ended up. And these type of answers are normally, if they're positive, we're saying we had a net displacement to the right. If your answer comes out being as negative, we had a net displacement to the left of the object. There's a big difference between displacement and distance. When you do areas under curves of a velocity function, you know we're doing this with regards to dt from one interval to the upper, and you're studying displacement, you examine the area in terms of net areas and you can expect either positive or minus answers. But when we're looking at distance, we're not looking at net effects anymore. We're talking about the total cumulative distance traveled, not where the object ended up, but how much traveling it did. If you know we're looking at here A1, which is generally positive, here A2, which is minus, you're going to view this as if it were positive with your distance calculation with regards to this integral procedure. Here you will pretend that the total distance traveled is basically the integral of this velocity function, but in an absolute value parentheses, so that way you can no longer get a negative answer and you will no longer be looking at a net displacement here, you'll be looking at a total effect. And the total effect is such that if you were to regraph it out, you don't have to, but you'd be looking at a situation which became something like this. A1 is positive, A2 is positive, now you're looking at the total cumulative effect of that distance. So keep all of this in mind, especially with regards to position, because the position gives us displacement and it gives us distance. So let's look at this question here. We have a velocity function 3t minus 5. We have an interval provided with regards to time from 0 to 3 seconds The velocity is units meters per second. We have to find the displacement and the distance. If at first this question seems difficult, it isn't, because you have to remember this. The integral of the velocity function will give you your position function. If you did definite integration, the position function can be manipulated or tweaked to give you both displacement and your distance. You should also think about graphing what you have provided. The 3t minus 5, you can easily graph it as a linear function. You know the interval is 0 to 3. If t is equal to 0, you have a minus 5 over here, 0 comma minus 5 y-intercept. If y is equal to 0 and you solve for t, you get a 5 over 3, 5 over 3 comma 0. Run a line through here. You know we're looking at an interval up to 3 right here from 0. So we're looking at an area which is relatively a negative area, and we're looking at an area which is relatively a positive, an A1 and an A2. When we're talking about displacements, we're thinking about net area. When we're talking about distance, we're talking about total area with absolute value involved in their absolute value. Always think back to this, that the integral of your velocity function will give you your position function. The position function can be tweaked or managed such that you can get both displacement and distance. If you take your velocity function from the interval 0 to 3, which is given 3t minus 5, and you know when you're talking about displacement, you can have positive or minus answers. When you're talking about distance, you should only have a positive answer. With regards to dt, you integrate this 3t squared over 2 minus 5t, and this is all basic polynomial integration. You calculate this with your calculator, and you get an answer of minus 1.5 meters. But what does this mean? It means that your object traveled 1.5 meters to the left, and that right there is your answer. From a position of 0, your net displacement is 1.5 to the left. It must have gone some distance this way, then it went more distance towards the left, hence you have that. That's your answer for A. The answer for B is not hard. You have to look at this in terms of two intervals, from 0 to this point right here, and from this point right here to here, and I've given you these points. And think about total area with regards to this function, and you have to bring absolute value into your velocity function, absolute value. From 0 to this 5 over 3, I have an area which is negative, therefore I'm thinking about this. Then from 5 over 3 to 3, I have already an area which is positive, so no absolute value is involved. I just have to do these two integrations with this equation right here over the intervals, and I'll get a good answer. So let's bring everything in. It's 3t minus 5 and dt, plus here we have 5 over 3 and then 3 and 3t minus 5 dt. And you know this right here is easy, definite integration. Of course we have to bring absolute value in all of this, we shouldn't forget that. We'll have 3t squared divided by 2 minus 5t, all in absolute value, from 5 over 3, 0 plus, let's come down over here. We'll have 3t squared, this right here is not an absolute value, it's just a regular circular, parentheses minus 5t, from 5 over 3 to 3. We have to do the cumulative sum of these. This, whatever, if comes out being a minus, you change it into a positive and you add it to this. It will bring our total distance right over here. I'll calculate it and I'll put it down. From the first part, I get a minus 4.166 repeating in absolute value, which will become a positive 4.166. From the second part, we have to do that calculation. Let's post it. Here I get it. 2.666 repeating. The cumulative area, when you add all of these, positive 4.166 because of the absolute value, plus 2.66, and let's put that answer. I get 6.833 repeating meters, and that right here will be my total distance traveled, 6.833 meters. So keep in mind over here, when we're dealing with the velocity function and we integrate it, we get the position. If you do the net area effect, you're calculating displacement. But if you do the total area effect, such that you take these negative areas and you hit them with absolute value, or you take this equation, you could have just, if you wanted, you could have just taken this equation, I'm going to put it right over here, done 3t minus 5, and just put a minus outside it. You would have ended up getting the same effect as you did with this. Absolute value of this is equal to this, minus with 3t minus 5 in parentheses over that interval, you would get the same thing. Anyhow, when you do the absolute value calculation and you convert all these negative areas into positive areas and you add all of these positive areas, you get the distance. Graphically, what you would be looking at over here, I'll show it to you right over here. It would be that same curve. It would have been pushed up like this from 0 to 5, and now this is what you would be looking at now. That would be A1 positive area and A2 positive area, and here you'd be getting your total distance. So we'll end our video with this question because I want to keep the video short, to the point, and maintain your level of interest. We have here an acceleration question, a function which is provided in terms of its acceleration. A of t is equal to t plus 4, and you know we have provided here the initial velocity being 5 meters per second. We have a time interval from 0 to 10, including 10. We have to find the velocity function, and we also have to find the distance traveled. When you see a question such as this and you're given the acceleration and now you have to find the velocity, the first thing coming in your mind should be this, that the integral of the acceleration function is always equal to the velocity function. So if you integrate your acceleration function, you'll get your velocity function. So let's continue with that procedure. We'll do a quick graph over here. T plus 4 is our graph. If t is equal to 0, we have an intercept in terms of y, 0 comma 4. If y is equal to 0, we have here minus 4 comma 0. So we're basically looking at a graph which looks something like this, but we're going from 0 up to, let's just say, 10. We're looking at this part right over here. We have absolutely no area which is here in terms of a negative quadrant. Everything is positive, so that's good. Let's integrate this because we have to find velocity function. If you integrate this acceleration function, we have t plus 4 dt. We can just keep the intervals out for now. We'll end up getting t square over 2 plus 4t, but then we also know that the initial velocity at time 0 is always 5, which means that from the time that this object was examined in terms of its acceleration study, it had an initial velocity of 5, and this right here, t square over 2 plus 4t plus 5, would give you your velocity function, and your answer would have been provided in meters per second. So if supposedly the question were to ask now a modification of this, find velocity, let's just say at time 5 seconds, and let's find velocity at time 10 seconds, it wouldn't be hard. You would take this velocity function you have and put 5 over there, and you get your speed at 5 seconds, and you can do the same thing with 10 and get your speed at 10 seconds. And let's just do it. When you put 5, you just put 5 in place of t. You have 25 divided by 2 plus 20 plus 5. There you get 37.5 meters per second for 5 seconds, and for 10 you just put 10 in place of t and you solve it, and then for that you get 95 meters per second. And it makes sense. You have an object that's accelerating, which means that there's a change in the velocity over time. That's what acceleration is, right? Over a period of time you have a change in that velocity, so as the time progresses, the velocity of that object will certainly increase over time because you have a linear function with a positive slope. Let's look at this distance traveled. How can we do that? Well, when we have the velocity function given, you know, when the velocity function is given and you do the integration of the velocity function, right, you're going to get the position function, and you know the position function can give you displacement and can give you distance. Displacement is the net effect of the positive and the minus areas. Distance is the cumulative effect of all the areas involved, with the negative areas being converted into positive by means of absolute value. If you were to integrate this, you would have the distance traveled, and you know you'd be looking at everything over the interval 0 to 10 seconds because you have 0 to 10 seconds. Let's do the integration of t square over 2, which t square over 2 plus 4t plus 5. We'll integrate this from 0 to 10 with regards to dt because the velocity integral gives you your position function. When you integrate this, you get t cubed over 6 plus 4t square over 2, which is no different than just saying 2t square, plus 5t from an upper interval of 10 seconds to a lower interval of 0. Plug in the 10s, putting the zeros is meaningless. Do your definite integration and present your answer. And the answer would be here 416.666 repeating meters. And that would be your total distance traveled over this interval 0 to 10 for an object which has an acceleration represented by the function t plus 4 having an initial velocity of 5. Remember, many of these questions come in play in physics, especially when you're doing physics with calculus. And these are how you present those type of questions, and these are how you solve those type of questions. In summary, when you're dealing with position, velocity, and acceleration, and you have these questions presented before you and you kind of go blank and you forget how you do them, remember it in this way. If you have a position function and you do its derivative, because this is how I've learned to do it, and it's relatively foolproof in my opinion, you're going to end up with the velocity function, which is also equivalent to the derivative of this position function, everything with respect to time. If you take the integral of your velocity function, you'll end up at the position function, and from the position function you can talk about displacement, you can talk about distance. Distance is the total distance traveled, the cumulative effect of all the positive areas. Anything negative becomes positive. Displacement is always your net, where you end up with regards to object being either towards the right or left. With regards to displacement, you can have positive answers or you can have minus answers. Distance here is always positive. If you are provided a velocity function and you do its derivative, you end up at the acceleration function, which is also equivalent to the derivative of the velocity function. If you're given the acceleration function and you do its integral, you end up back at the velocity function. And from the velocity function, once this is known, you can easily progress into this, because you can see this right here goes that way in terms of the integral. Once you have the velocity, you can easily use the time values by means of the integration and start calculating distance and displacement. So remember this little cycle over here and it can really help you out. If at all, memorize it and it will be really beneficial. Thank you for watching this video. Have a nice day.